Okay. Web work, homework 10, question 18. Find the coordinates of the point xyz on the plane z equals 2x plus y plus 1, which is closest to the origin. There are two different ways that you can do this. One is finding the extrema of both variables. The first step of that is to find the three-variable equation. Now, since we're finding distance from the origin, you could find the square root of x squared plus y squared plus z squared, but the square root actually makes this pretty complicated. So if you, and you can prove this to yourself, if you have the square root of, if you're optimizing the square root of a function, and actually you can actually just use this function itself, x squared plus y squared plus z squared, and you can prove to yourself that anything that you plug in here, if you optimizing that, it's actually also going to optimize the square root. In the next step, you're going to plug in your two-variable plane solution for z. So now you've got f of xy is equal to x squared plus y squared, and then we entered 2x plus y plus 1 into z and squared. Now you could simplify this, but it turns out to be a lot easier to just leave it like that when you find your partial derivatives. Step 3 is to find your partial x and partial y. F of xy simplifies down to 2x, and then bring down the squared to make it 2x plus y plus 1, and then the derivative of the inside 2x is just 2. This simplifies out to be 2x plus 4y plus 4. Fy of xy will be equal to 2y plus, bring down the 2x plus y plus 1, derivative of y is just 1, and that simplifies to 4y plus 4x plus 2. Now, step 4, you're going to set both of those partial equations equal to 0 and solve so that you get one variable. In this situation, it works out very nicely because you've got a 4y in both equations, so you can just subtract one from the other. So you've got 10x plus 4y plus 4 equals 0, and you just subtract out 4x plus 4y plus 2 equals 0. And those will simplify to just 6x plus 2 equals 0. And then you can simplify that to find that x would be equal to negative 1/3. Okay, step 5. Now that you've found your x, you can use the partial equations to find y. You have your 10x plus 4y plus 4. You just plug in the negative 1/3, and you can simplify that, and you'll find that y is equal to negative 1/6. It's always a good idea to check by using the other partial. Just plugging in your x and your y to set it equal to 0, and you should get an equality out of that. In this case, negative 2 equals to 2. Step 6, you're going to use the plane equation that you had to find z. So z equals 2x plus y plus 1. You plug in your x and your y values, and you'll find that it's 1/6. In step 7, you use the second partials test. Now that you've got the solutions to your x, y, and z, you want to make sure that the solution that you have is actually a minimum. We said f of x of xy was 10x plus 4y plus 4, so f double x is just going to be 10, right, derivative of 10x. F of xy would be the derivative of the 4y, which would be 4. We said f of y was 4x plus 4y plus 2. F double y is the derivative of the 4y, which is 4. And then it's always a good idea to double check that your fxy is correct by doing fyx, which is the derivative of the 4x, which is 4. Now in this situation, since there aren't any variables in the second partials, it doesn't really matter that there's the particular solution, but it's always a good idea to take a look. And so we've got f double x is 4, fxy is 4, f double y is 4, and then you want to plug that into your second partials test. So you've got your f double x times your f double y, subtract out your fxy, and you end up with 24, which is greater than 0. Since f double x, which was 10, is also greater than 0, you're going to find, since f of xy is concave up, it will actually have a relative minimum at negative 1/3, negative 1/6. So now we know that that is the minimum. Okay, the second option, you can use Lagrange multipliers. The first step is to find your target and constraint 3-variable functions. So this is useful if you have several different variables that you can't really simplify into a 2-variable function. In this case, we're going to use the same f of x, y, z to be x squared plus y squared plus z squared. And then g of x, y, z, the constraint, that would be if you took z equals 2x plus y plus 1 and you just moved everything to the same side so that it's equal to 0. So your g is equal to z minus 2x minus y minus 1. Now in step 2, you're going to want to find your partials. Fx will be 2x, you just bring down the x squared. Fy, 2y, fz, 2z. G of x is, if you find the derivative of negative 2x, you get negative 2. The derivative of your negative y is negative 1. And the derivative of z is just 1. Okay, then in the third step, you're going to use your partials to find the gradients. Basically, you just plug it in so that you've got your partial x I plus partial y j plus partial z k. So 2xi plus 2y j plus 2zk, and then your gradient for g, negative 2i plus negative j plus k. In the next step, you're going to set your gradients so that they are some proportion of lambda to one another. So 2xi plus 2yj plus 2zk equals lambda times your gradient of g. Then you can set each one of those components, I, j, and k, so that they're equal to each other. So you've got 2x equals negative 2 lambda. Lambda is negative x. 2y is equal to negative lambda. Lambda is negative 2y. And then 2z is equal to lambda. So now I know that negative x is equal to negative 2y is equal to 2z, and I can solve them so that they are all, in this case I like to use in terms of x, so z is equal to negative x over 2, and then y is equal to positive x over 2. In the next step, you're going to solve your constraint equation for one variable. In other words, you're going to plug in the values that you found that z and y are equal to in terms of x. So you've got negative x over 2 minus 2x minus x over 2 minus 1 equals 0, and x once again will simplify to negative 1/3. In step 7, since we already have our x and y, or our z and y in terms of x, we can just plug in that x to directly find our y and z values. in step 8, you're going to want to solve your target equation for the values that you're given. The problem doesn't ask for this, but it's important to do that so that you can compare it to other locations on the plane in order to make sure that you actually have a minimum. In this case, you don't have an analytic answer like you have with the second partials test, where you can say, oh, this is, since it passes this test, you can say it's definitely a minimum. You just have to use other points on the plane to estimate it. In step 9, you're going to find solutions that are nearby, as I said, to ensure that you have a minimum. I try to use solutions where x is less than the number and where x is where x is larger than the number. So I have here x equals -1 and I let y equals -1. You solve for z, and then you plug in your f of x, y, z. So it's -1 squared plus 1 squared plus -2 squared, which is 6. That's greater than the solution that we found, 0.1667, etc. Then I found x, if I let x equal -1 and y equals 0. And then once again I plug it into the equation, and it still turns out to be more than our minimum. I let x equal to 0 and y equal -1, and I also let x equal 0 and y equal 0. In all of these situations, you have the solution that you're finding turns out to be less than what we have considered our minimum. So we can reasonably expect that this is in fact a minimum and not either a saddle point or a maximum.